Welcome to the Design and Analysis of Algorithms course. I'm Madhusudan and I will be giving some guest lectures in this course, including this introduction. Most of the lectures will actually be given by Professors Madhavan Mukund and Kavi Mahesh. Okay, so let's see what this course is about. So I would like to motivate this course for you, try to tell you why you should be interested in this course. And also tell you a bit about what actually we'll see in this course. And in particular, there are these three words here, which are design, analysis, and algorithms. And we'll see what each of these three words will mean in this course. So in some sense, it all started in India around 500 AD. By 500 AD, the Indians knew how to use a zero as a number, and they were the first in the world to really use zero as a true number. And they defined, or they invented this decimal positional number system that we still use today. So if I wanted to write 5023, the fact that I can use a decimal numbering system for this goes back to about this time. So the crucial thing that you need in a positional number system is that the position of a digit in this representation, namely 5 is in the thousandth place, that position determines the value that it contributes to the number, right? And 0 is crucial for this because you need to say that a particular place does not contribute anything. And it turns out that if you have this kind of positional number system, you can do algorithms or procedures for calculating numbers and functions on numbers much easier than you would be able to calculate, let's say, using a Roman number system, right? If you had, if you represented 14 like this and so on, it would be very hard to calculate, let's say, add two numbers, right? But of course, if we have the decimal positional number system, we can add, and these were in fact the first algorithms ever discovered. And what happened was that this zero and the numbering system traveled to Iraq, in Baghdad, where Al-Khwarizmi was a Persian mathematician, astronomer, became very interested in this. And in fact, the word algorithms comes from Al-Khwarizmi because he propagated it to the West. Right. So this he wrote this book called On the Calculation with Hindu Numerals around 825 AD, which was very influential in the West, and in particular in Italy. Fibonacci was a mathematician who was very much interested in this system, and he propagated it, and that's how we come to use this today. So the very first algorithms were really algorithms on numbers written using decimal notation. So if I had this and this number, I could add these two numbers and I would get this number, right? So the very fact that I'm adding this and doing the carry and everything is an algorithm, and these were the first algorithms ever known, right? And later on, any procedure to do some task became known as an algorithm, not just algorithms on numbers. The simplest way to look upon an algorithm is to view it as a recipe in cooking. So a recipe, like the bisi bele baat recipe we have here, is a sequence of instructions where each instruction is fairly simple that a cook can follow. Unfortunately not me, but a cook can follow and end up producing this dish. Right? An algorithm is similar. It's a sequence of instructions. Each instruction you can make a computer to do that, and then in the end the computer will end up solving the problem. So more formally, you can think of an algorithm as an effective method expressed as a finite list of well-defined instructions for calculating a function. Right? These instructions should be doable by a computer, and we require that this is a finite list of instructions. Right? So in general, problems will have infinitely many instances. For example, if you take the problem of addition, right, then there are many instances like 53 plus 17, 19 plus 22, and so on. But we want to give these instances to a single algorithm that has finite description. This is a core concept in computer science, that algorithms are basically finite tree descriptions of ways to solve an infinite class of instances. A more formal definition was actually given by Alan Turing, and it turns out that these are precisely the notion of algorithms that one needs, using this concept called a Turing machine that you will learn in your theory of computation course. A Turing machine is basically a machine where the instructions are extremely simple, that they are definitely realizable in the physical world, and therefore Turing machines are obviously algorithms. We will not use Turing machines in this course. We will instead use a much more informal notation. So in this course, instructions are basic steps that a program can do, definitely. For example, if I have an array and I have an index into the array to get to the next element in the array, I know a computer can do that. I know that a computer can add numbers and so on. Though we will be very precise in saying what an algorithm does, we will actually be independent of the programming language that is used. So when you want to solve a computational problem, the algorithm is actually an abstraction of the program that you finally want to design. The algorithm is not tied to any programming language, right? So at this abstract level of the algorithm, you can do design and analysis, right? You can do a time analysis to figure out how fast the program will run. You can do analysis to see how much space it would take and so on. And once you've designed the algorithm and it meets your expectations, right, you can always go ahead and program it in any programming language of your choice, like C or Java or C#. Okay. So though we will not tie ourselves to any programming language per se, we will follow the imperative programming style, because it turns out that imperative programming is much easier to analyze for time complexity and so on. So one way to teach an algorithms course would be to lay down various problems in computer science that we have seen, let's say sorting, searching, and so on, right? And for each of these problems, I can give you the best algorithms that we know, right? And so on, right? And I can just teach you how to solve these problems. But if you go out in the real world and you come across a problem that you want to solve, it may not be one of these problems that we have taught you how to solve, right? And therefore, this might be useless, right? Thankfully, it turns out that many of these algorithms have underlying design principles. So a design paradigm is an underlying design principle that forms the basis of many algorithms. A design principle really cuts across problems, right? As a set of algorithms have such a design principle as their basis of computational thinking, right? For example, divide and conquer is one such design paradigm, right? So in order to tell you what a design principle really is, I'm going to introduce you to a puzzle called the Towers of Hanoi, and using the solution to this Towers of Hanoi problem, we will see what a design principle is. Okay, so we're going to demonstrate the notion of design through a simple puzzle. So in this puzzle called the Towers of Hanoi, or the Towers of Brahma, or the Brahma cone, I have 3 spindles here, and I have a set of discs that I borrowed from my 2-year-old son's toy collection. The discs are of varying sizes. The blue is the largest and red is the smallest, and as you can see, it's arranged such that the smaller discs are on top of the larger discs. The goal of the game is to make all these discs go to the last spindle on my right to your left, right? So this is the 3rd spindle for me. I want to move all the discs from the first spindle to the last spindle. And one of the restrictions I have is that at any point I cannot put a larger disk on a smaller disk, right? And also I can move only one disk at a time. So for example, if I take this disk and I move it here, the second disk when I take, I cannot put this on this because the orange disk is larger than the red disk. So I can only put this here, right? And the question is, can I somehow, through a sequence of moves, can I move all the disks from the first spindle to the last spindle so that in the end I have all these disks on the last spindle like this. Okay. So the legend has it that somewhere in Varanasi there are people who are doing this for 64 golden disks, right? Gold disks. And once they finish moving them to the third spindle, the world is supposed to end. As we will show later in this course, even if they can move one disk in 1 second, right, this will take a terribly long time, and it's much longer than the time it will take for the world to end. Okay, so let's start this with doing it for small number of disks. So let me just take 2 disks and solve the puzzle. Right, now what we are looking for is an algorithm which can move any number of disks from the first spindle to the last spindle. For any n, if I start with n disks on the first spindle, I want to end up with the n disks transported to the last spindle. Okay, but the method itself is going to be only a finite tree description. So I want one single method which will kind of work no matter how large n is, and that is the notion of an algorithm. Okay, for 2 disks is very simple. I just move this here, I move this one here, and then I move this here, and I'm done. Okay, so 2 is clearly solvable. Now let's move to 3, and it's not hard to see that 3 is also can be solved. I move this red one here first, and then this orange one here. Then I can move this red back here because it's smaller, and then I can move the yellow here, move the red back to the first spindle, take the orange, put it on the right, and then I'm done. Okay, so now let's do it for 4 spindles, but you can pause the video and try to solve this by yourself. You can try how to do this for 4 disks, and you don't need this apparatus really. You can just work it out on paper. You can just draw the spindles and do the moves. Okay, so I hope you did it for 4 disks. I won't show you the solution for 4 disks, but I'll actually do the solution for 5, which is much longer. I'm just going to do the solution. Yoo-hoo! That went through. So thanks for the applause. So as you notice, it was a very long sequence. Okay, it was actually 31 moves, and so it's a hard sequence. And somehow, I was able to do it for 5. But the question is, can you do it for any n? What happens if n is 6, 7, 1,000? How do we solve this, right? So if you look at the solution, it's kind of hard to understand what the general mechanism of showing this is, right? But there is this general design principle which you can use to solve this puzzle in general, right? And that is called recursion, and it's something which we use all the time in computer science, right? And the idea of recursion, or divide and conquer, is that you build a larger solution by using smaller solutions. Okay, so the idea is that you assume that you have some magical elf or fairy who can solve this problem for a smaller value of n,
right? And then you use that to solve the larger value of n. Okay, so this recursion fairy, or recursion devi if you will, right, you can use her to do smaller problems, okay, and then you have to solve the larger problem. So in this, I'm just going to demonstrate for 5. I'm going to assume that I have a recursion devi who can transfer 4 disks from one spindle to another, right? So then what is the solution is that I call this recursion devi, right, and ask her to transfer all these 4 disks into this one, into the second spindle, right? And there's some way to do that, okay? I don't care how she does it, right? But after she does it, I can go and move this large disk to the last spindle, right? And then I call the recursion devi again and I ask her to move all these 4 to this one, okay? So by using 2 calls for help to this recursion devi, I can solve this puzzle. And the reason why this is actually a solution is because when you're calling the recursion devi to transfer this, right, even if no matter what the recursion devi does, if she puts some disks here, it is always valid because this disk is much larger than, larger than all these disks, right? So whatever the recursion devi does to transfer this from the first spindle to the second is actually correct. And so this is how you build a recursive solution.
So let's see how to solve the towers of Hanoi problem for n disks where n is greater than or equal to 2, let's say. Okay, so I have n disks here, and n can be anything. So the way to solve this is to first call the recursion fairy, or the recursion devi, right? And the recursion devi will solve problems of size n-1. So you can call the recursion devi and ask her to transfer the top n-1 disks from the first spindle to the second spindle. So she would do that. You'll have the largest disk on the first spindle and the other n-1 disks on the second spindle, right? And then you can transfer the largest disk from the first spindle to the last spindle, right? So you will get this configuration, and then you can call the recursion devi again and ask her to take this n-1 disks on the second spindle and transfer them to the third spindle. And that would result in this configuration where the largest disk is in the bottom there, and the other n-1 disks go on top, and you've solved the problem. The solution for n will call the recursion fairy for n-1, which will call the recursion fairy for n-2, and so on. So really it'll come down to n equal to 1. For n equal to 1, you need to show that the recursion devi does exist, right? And this is called the base case. But for n equal to 1, clearly the recursion devi exists. You don't need to call other recursion devis, right? If you have only one disk, you can easily transfer it directly to the third spindle, right? It turns out that this technique of recursion can be used to solve real problems in computer science, not just puzzles. So for example, let's say that you want to sort a list of n numbers. You're given n numbers in an array and you want to arrange them in ascending order. Then the recursive way to do this, or the divide and conquer way to do this, is to divide the array into 2 parts, let's say A and B. Okay, and then since these arrays, the left and the right arrays are smaller, I can call the recursion devi on the left half of the array and ask her to sort that, and I'll get this sorted list A prime. And I can call the recursion devi on the second half and ask her to sort that, and it'll result in this array B prime, right? Now these are 2 sorted lists, and all I have to do is merge these 2 sorted lists into a single long sorted list. And this turns out to be a much easier problem, so you can do that, right, resulting in sorting the entire array that you were given in the beginning, right? And this sorting algorithm actually is called merge sort, and you will see this later in the course, and it actually turns out that it's an optimal sorting algorithm that uses divide and conquer. So when you look at a recursion problem, right, a recursive solution, right, you have a large problem and you divide into 2 smaller solutions, and these get divided into smaller problems and so on, right? And in some sense you get a recursion tree of subproblems, right? Now it turns out that in certain cases the subproblems that get generated across these paths are not all different, but some of them actually are the same. So maybe, for example, these two subproblems are really the same subproblem, right? And so it turns out that instead of solving them twice or thrice every time you meet it, right, you can actually memorize the answer, right? You memorize or remember the answer for the subproblem, so that the next time you hit the subproblem, you don't solve it again, right? And this, in general, leads to faster algorithms, right? And in fact, this technique is called dynamic programming, which is a design principle as well, right? A lot of algorithms actually follow the dynamic programming principle to get efficient algorithms.